For centuries, humanity has gazed upon the night sky, believing that what we saw was the entirety of the cosmos. Our understanding was limited by the naked eye, leading to a profound, yet incomplete, view of our place in the universe. This perspective, though poetic, was a fundamental misunderstanding, an illusion of cosmic simplicity that obscured a far more complex and bizarre reality waiting to be revealed. The universe is not what you think. It's a realm governed by forces and entities we cannot see, comprised of structures so immense they defy our imagination, and operating under rules that often contradict our intuitive grasp of reality. Prepare to dismantle your preconceived notions, because the cosmic revelations we're about to explore will fundamentally alter your perception of existence itself. Our journey begins with scale, a concept so vast it typically breaks our minds. We live on a tiny planet orbiting an average star in the Orion arm of the Milky Way galaxy. Yet, even within our own galactic neighborhood, distances are measured in light years, a unit representing the distance light travels in 1 Earth year. That's nearly 6 trillion miles. The Milky Way galaxy itself spans roughly 100,000 light-years in diameter and contains an estimated 200 to 400 billion stars. Each one could potentially host its own planetary system. To truly comprehend this, imagine our sun as a single grain of sand on a vast beach, where the entire beach represents just our galaxy. And our galaxy is just one of billions. The observable universe, the portion cosmic light has had time to reach us since the Big Bang, is estimated to contain at least 2 trillion galaxies. Not billions, but trillions. Each a sprawling island of stars, gas, and dust, separated by unimaginable cosmic voids largely empty of matter. The cosmic web represents the largest known structure in the universe. Galaxies are not randomly distributed. They are arranged in a vast, intricate network of filaments and clusters, separated by immense, empty voids. This web-like structure is a direct consequence of the universe's early evolution, shaped by gravity over billions of years. But this immense observable universe, with its trillions of galaxies, is merely a fraction of the total universe. Due to the expansion of space, much of the cosmos has expanded beyond our light horizon, meaning its light will never reach us. The true extent of the universe might be infinite, or at least many orders of magnitude larger. This seemingly infinite expanse isn't static, it's dynamic. The fabric of space itself is stretching, carrying galaxies further apart. This expansion isn't galaxies moving through space, but space itself expanding between them, like points on an inflating balloon. This critical distinction explains why distant galaxies appear to recede faster. This mind-bending expansion began with the Big Bang, not as an explosion in space, but as an expansion of space from an incredibly hot, dense state. The cosmic microwave background radiation, or CMB, is the afterglow of this primordial fireball, a uniform glow of microwave energy permeating the entire universe. The Big Bang theory, while incredibly successful, doesn't explain everything. It leaves fundamental questions unanswered, like what existed before the Big Bang or what triggered this rapid expansion. These mysteries push the boundaries of our understanding, hinting at even stranger cosmic realities beyond. Many scientists now believe an epoch called inflation occurred a tiny fraction of a second after the Big Bang. During this period, the universe expanded exponentially, faster than the speed of light, smoothing out irregularities and planting the seeds for future larger-scale structure. It's a truly bizarre, yet necessary, addition to the cosmic narrative. But the greatest mystery isn't what we see, but what we don't see. When astronomers measure the gravitational effects within galaxies and clusters, they find far more mass than can be accounted for by visible matter, stars, gas, and dust. This missing mass is called dark matter, and it makes up about 27% of the universe's total mass-energy content. Dark matter does not emit, absorb, or reflect light, rendering it entirely invisible to telescopes. Its presence is inferred solely through its gravitational interaction. Imagine a powerful, invisible scaffold upon which the visible universe is built, guiding the formation and movement of galaxies and larger-scale structures. Scientists hypothesize that dark matter might consist of exotic, as-yet-undiscovered particles that interact very weakly with ordinary matter. Experiments deep underground and in particle accelerators are actively seeking to detect these elusive particles, hoping to finally uncover the nature of this dominant cosmic component. However, dark matter is just one piece of the invisible puzzle. Even more perplexing is dark energy, which constitutes roughly 68% of the universe's total energy density. It's the mysterious force responsible for the accelerated expansion of the universe, pushing galaxies apart at an ever-increasing rate. Think of it, not only is the universe expanding, but it's speeding up. This observation directly contradicts what gravity alone would do, which is to slow down expansion over time. Dark energy acts as a kind of anti-gravity, a pervasive force inherent to space itself, driving the cosmic acceleration. The simplest explanation for dark energy is a cosmological constant, first proposed by Albert Einstein, representing the energy density of empty space itself. But if space itself has inherent energy, its vacuum fluctuations would be astronomically higher than observed, creating a monumental discrepancy. Other theories suggest dark energy could be a dynamic fluid called quintessence, or even arise from modifications to gravity on vast cosmic scales. The leading edge of cosmology grapples with understanding this enigmatic force, whose nature will redefine our ultimate fate. The accelerating expansion driven by dark energy implies a future far different than once imagined. Instead of a big crunch, where the universe collapses back on itself, or a big freeze, where it slowly cools, we face a big rip or continued exponential expansion leading to ultimate cosmic isolation. If the universe continues to expand and accelerate, galaxies will eventually recede beyond each other's observable horizons. Our cosmic neighborhood will shrink, leaving future civilizations unable to even detect other galaxies, believing their own island universe is all that exists. A truly lonely cosmic dawn. Now let's delve deeper into the fundamental nature of reality itself, space-time. Einstein taught us that space and time are not separate entities, but are interwoven into a single, four-dimensional fabric. Gravity isn't a force pulling objects, but the curvature of this space-time fabric caused by mass and energy. Imagine a bowling ball placed on a stretched rubber sheet. It creates a dip. A marble rolled nearby will curve towards the bowling ball, not because the bowling ball is pulling it, but because the sheet itself is distorted. This is fundamentally how gravity works, shaping the paths of planets, stars, and even light. This means massive objects like galaxies warp spacetime so significantly that they can bend light from distant sources. This phenomenon, called gravitational lensing, allows us to see objects that would otherwise be too faint or too far away. It's one of nature's most powerful cosmic telescopes. Time itself is not absolute. Einstein's theory of special relativity revealed that time passes at different rates for different observers, depending on their relative speed. The faster you move, the slower time passes for you relative to a stationary observer. This phenomenon is known as time dilation. Atomic clocks flown on airplanes or onboard the International Space Station confirm this. They return to Earth showing a minuscule but measurable time difference compared to clocks on the ground. This isn't just theoretical. It's a fundamental aspect of reality, with practical implications in technologies like GPS. General relativity takes this further. Gravity also affects time. Time passes more slowly in stronger gravitational fields. For instance, time runs slower at the surface of Earth than it does in orbit, and drastically slower near a black hole. This means if you could stand on a neutron star, which possesses immense gravity, time would pass significantly slower for you compared to someone far away. If you visited a black hole's event horizon and returned, billions of years might have passed on Earth. Your journey would be a true trip into the future. The concept of horizons also extends to cosmology. The particle horizon defines the maximum distance from which particles could have traveled to the observer in the age of the universe. It's the edge of our observable universe, a limit imposed by the speed of light and the universe's age. Beyond the particle horizon lies the unknown, regions from which light simply hasn't had time to reach us. As the universe ages, this horizon expands, slowly revealing more of the cosmos, but never the whole picture if the universe is truly infinite. The event horizon, in the context of a black hole, is a boundary beyond which events cannot affect an outside observer. Once anything, including light, crosses this point, it is trapped forever by the black hole's inescapable gravitational pull. It's a point of no return. Black holes are perhaps the most mind-bending objects in the universe. They form from the gravitational collapse of massive stars, crushing matter into an infinitely dense point called a singularity, where the laws of physics, as we know them, break down. At the heart of a black hole, according to general relativity, is a singularity, a point of infinite density and zero volume. Here, spacetime is stretched infinitely, and the laws of physics cease to apply, offering a tantalizing glimpse into realms beyond our current comprehension. There are different types of black holes. Stellar black holes are a few times the mass of our Sun. Supermassive black holes, like Sagittarius A at the center of our Milky Way, can contain millions or even billions of solar masses. These cosmic behemoths anchor galaxies. Black holes are not cosmic vacuum cleaners. They don't suck everything in. If our Sun were instantly replaced by a black hole of the same mass, Earth would continue to orbit it exactly as it orbits the Sun now. You would fall in only if you got too close, beyond the event horizon. Yet black holes are incredibly powerful. Their immense gravity heats enthralling matter to millions of degrees, causing it to emit X-rays and other radiation as it spirals into the event horizon, making them detectable despite their inherent darkness. The information paradox is another major puzzle. Quantum mechanics suggests information cannot be destroyed. But if matter falls into a black hole and the black hole eventually evaporates via Hawking radiation, what happens to the information contained within that matter? Is it truly lost forever? Stephen Hawking proposed that black holes emit a faint thermal radiation, now known as Hawking radiation, due to quantum effects near the event horizon. This radiation causes black holes to slowly lose mass and eventually evaporate over unfathomably long timescales. The mystery of black hole information is a battleground between general relativity and quantum mechanics. Resolving it could lead to a unified theory of quantum gravity, one of the holy grails of modern physics, bridging the gap between the very large and the very small. Speaking of the very small, let's venture into the quantum realm, where the cosmic rules become even stranger. At the subatomic level, particles behave in ways that defy classical intuition, demonstrating wave-particle duality and appearing in multiple states simultaneously. Quantum fluctuations, fleeting appearances of particles from empty space, are not just theoretical curiosities. They are believed to have played a crucial role in the early universe, specifically during inflation, seeding the tiny density variations that eventually grew into galaxies. The universe, on its grandest scale, might be thought of as a quantum system. The wave function of the universe describes all its possible states, and its evolution is governed by quantum laws. This is a profound shift from a deterministic classical view. Another mind-bending concept, the holographic principle. This audacious idea suggests that all the information contained within a volume of space can be encoded on its boundary, much like a hologram. Our three-dimensional universe could be a projection from a two-dimensional surface at its edge. This principle arose from trying to unify gravity and quantum mechanics, particularly in the context of black hole thermodynamics. If true, it implies a fundamental level of reality is far different and perhaps simpler than the layered, three-dimensional space we perceive. The arrow of time, the undeniable progression from past to future, is another cosmic enigma. While the fundamental laws of physics are largely time-symmetric, the universe itself has a clear direction. From the low entropy state of the Big Bang to an ever-increasing state of disorder. This increase in entropy, the second law of thermodynamics, dictates the universe's ultimate fate, heat-death, where all energy disperses uniformly, leaving a cold, dark, inert cosmos with no available energy for any processes. Let's turn to life beyond Earth. For decades, the search for exoplanets was limited, but now thousands have been discovered, many within the habitable zones of their stars, offering tantalizing possibilities for liquid water and potentially life. The sheer number of stars and galaxies suggests that life in some form might be abundant. The fundamental building blocks of life, amino acids, organic molecules, have been found in comets, asteroids, and nebulas, implying that the raw ingredients are widespread. The Fermi paradox asks, if extraterrestrial life is common, why haven't we detected it? Possible explanations range from our current technological limitations to the vastness of space to the scary Great Filter hypothesis. The Great Filter suggests there's a barrier to the emergence of complex, intelligent life, perhaps in our past, explaining why we haven't seen others, or terrifyingly, it lies in our future, a challenge we may not overcome, preventing any civilization from becoming spacefaring and long-lived. The universe is a cosmic laboratory for the fundamental forces, from the strong nuclear force binding protons and neutrons to the weak force governing radioactive decay, electromagnetism, and gravity. These four forces dictate everything we observe, from the smallest atom to the largest galaxy. The standard model of particle physics describes the fundamental particles and three of these four forces. Still, gravity remains stubbornly outside this elegant framework, leading physicists to seek a theory of everything that unifies all forces and matter. This quest often leads to theories like string theory, which posits that fundamental particles are not point-like, but tiny, vibrating one-dimensional strings. Different vibration patterns of these strings correspond to different particles, including the graviton, the hypothesized carrier of gravity. String theory, however, requires the existence of extra spatial dimensions beyond our perceived three spatial and one temporal dimension. These dimensions are thought to be curled up or compactified at incredibly tiny scales, making them imperceptible to us. These extra dimensions could offer profound implications, perhaps affecting gravity at small scales or even providing pathways between different universes in a multiverse scenario. They are a truly mind-altering concept, shifting our understanding of spatial reality. Let's confront one of the most provocative ideas, the multiverse. The Big Bang of our universe might not have been a singular event, but one of countless such events, leading to an infinite number of universes, each with its own physical laws, constants, and histories. There are various levels of multiverse theories. Level 1, the infinite universe, suggests if our universe is truly infinite, then everything that can happen will happen an infinite number of times, including exact copies of ourselves, just impossibly far away. Level 2, the pocket multiverse, or bubble universes, arises from eternal inflation. Here, inflation never truly ends, but continues in patches, spitting out new bubble universes, each with potentially different physical laws and fundamental constants. This level helps explain the fine-tuning of our universe. Why are the physical constants so precisely calibrated for life? In an infinite multiverse, where every possibility is realized, our existence simply arises in one of the universes where conditions are just right. Level 3, the many worlds interpretation of quantum mechanics, proposes that every quantum measurement or decision causes the universe to split into multiple parallel universes, each representing a different outcome. It's a continuous branching of reality with mind-boggling implications. Level 4, the ultimate multiverse, includes all mathematical structures that are consistent. If a mathematical structure describes a universe, then that universe truly exists. This is the most abstract and encompassing form of the multiverse, where reality is synonymous with abstract mathematics. The multiverse fundamentally changes our understanding of uniqueness. Our universe, our laws of physics, our existence might not be special or unique at all, but merely one ripple in an infinite cosmic ocean of possibilities. While speculative, the multiverse offers potential solutions to deep cosmological puzzles, such as the initial conditions of the Big Bang or the problem of fine-tuning. It's a concept that challenges the very notion of a beginning and an end to existence. Let's consider the concept of extraterrestrial intelligence, not just life. The vastness of space, combined with the extreme age of the universe, means that if other civilizations exist, they could be unimaginably advanced, perhaps millions or billions of years ahead of us. The Kardashev scale categorizes civilizations by their energy consumption. Type I uses all energy on their home planet. Type II harnesses their star's entire output, perhaps with a Dyson sphere. Type III controls the energy of an entire galaxy. We are currently a Type 0 civilization. Imagine what a Type III civilization could achieve. They would possess unfathomable power, manipulate entire stars, potentially even traverse vast intergalactic distances. Such beings would exist on a cosmic scale, capable of feats we currently deem impossible. Such advanced civilizations might employ technologies beyond our current comprehension, perhaps using quantum entanglement for instantaneous communication or manipulating spacetime itself for travel, bending the very fabric of reality to their will. The search for technosignatures, evidence of technology, is a growing field. This includes looking for unusual radio signals, laser pulses, or even atmospheric compositions that suggest artificial origins on exoplanets. Even if we are alone, the implications are profound. It would mean our conscious existence is an immensely rare and precious thing, endowing humanity with a unique responsibility to protect and foster life in this corner of the cosmos. The universe is also a dynamic dance of cosmic behemoths. Neutron stars are the incredibly dense remnants of supernova explosions, packing more mass than our Sun into a sphere only 20 kilometers wide. A sugar cube of neutron star material would weigh billions of tons. Some neutron stars are pulsars, emitting precise, rhythmic pulses of radio waves as they spin, like cosmic lighthouses. Others are magnetars, possessing magnetic fields trillions of times stronger than Earth's, so powerful they could potentially strip electrons from your atoms at a distance. Then there are gamma-ray bursts, the most powerful explosions in the universe, believed to originate from the collapse of massive stars into black holes or the merger of two neutron stars. They release more energy in seconds than our Sun will in its entire 10 billion-year lifetime. These events are catastrophic, capable of sterilizing planets in distant galaxies if their powerful beams happen to sweep past. They remind us that the cosmos is a violent, unpredictable place, full of forces that dwarf human comprehension. The universe is not just vast and violent, but also exquisitely beautiful and self-organizing. From the intricate patterns of nebulae, the stellar nurseries where new stars are born, to the graceful spirals of galaxies, cosmic aesthetics abound. The life cycle of stars is a grand cosmic dance of creation and destruction, recycling matter across billions of years. Stars forge heavier elements in their cores, then disperse them in supernovae, providing the raw materials for new stars, planets, and even life itself. Every atom in your body, except for hydrogen and some helium, was forged in the heart of a star or in a supernova explosion. We are literally stardust, intimately connected to the violent and creative processes of the cosmos. Let's consider the concept of time in cosmology, beyond mere duration. Is time fundamental or an emergent property of the universe? Some theories propose time didn't exist before the Big Bang, or that it might even flow differently in other regions of the multiverse. The Manemind's interpretation of quantum mechanics, a variation of many worlds, suggests that it's consciousness itself that causes the quantum wave function to collapse, leading to an infinite number of subjective minds experiencing different realities. This idea links the observer directly to the construction of reality, implying our conscious experience might be far more intertwined with the fabric of the universe than we typically imagine. The universe may truly exist because we observe it. The principle of mediocrity suggests that Earth and humanity are not special or unique in the cosmos. Given the vastness of the universe, our existence is likely typical, not exceptional, reinforcing the probability of life elsewhere. However, the rare Earth hypothesis argues the opposite. It posits that the confluence of specific conditions necessary for complex life, plate tectonics, a large moon, a stable star, Jupiter's gravitational shielding, is incredibly rare, making Earth a true cosmic rarity. The truth likely lies somewhere in between, but the debate powerfully shapes our search for life and how we perceive our own significance in the vast cosmic theater. Are we alone, or one of many, perhaps even average? Let's explore the largest structures known. While the cosmic web organizes galaxies, scientists have also identified large quasar groups, vast collections of quasars spanning billions of light years, which challenge our models of cosmological homogeneity. There's also the puzzling cold spot in the cosmic microwave background, an unexpectedly large and cold region that doesn't fit neatly into our standard cosmological models. It could be a supervoid, a gravitational anomaly, or even a hint of another universe. These anomalies are crucial. They represent the frontiers of our knowledge, where existing theories might break down, pushing scientists to develop new models and hypotheses that could unveil even more profound cosmic truths. Consider the ultimate age of the universe. Current estimates place it at 13.8 billion years, but this is the age of our observable universe since the Big Bang. If inflation stretched space exponentially, regions beyond our horizon could be far older. And what about the cosmic dust-up surrounding the Hubble constant? Different methods of measuring the universe's expansion rate currently yield conflicting results, hinting at new physics or unaccounted-for factors in our cosmic equations. This discrepancy, though small, is significant. It suggests we might not fully grasp all the parameters governing cosmic expansion, possibly hinting at new fundamental particles, fields, or even a more complex form of dark energy. The universe is finely tuned. The precise values of fundamental constants, like the strength of gravity or the mass of an electron, appear to be extraordinarily precise for the emergence of life. If they were even slightly different, stars might not form, or atoms wouldn't be stable. This fine-tuning problem is a profound enigma. Is it sheer coincidence, evidence of a multiverse where every possibility plays out, or a hint of deeper, underlying principles and connections that we are only beginning to fathom? The pursuit of knowledge in cosmology is never-ending. Every answer often reveals a deeper, more mind-bending question. The universe continually surprises us, proving itself to be far more extraordinary and mysterious than we could possibly conceive. Consider the future of cosmic exploration. Next-generation telescopes like the James Webb Space Telescope are piercing deeper into the early universe, revealing galaxies from just a few 100 million years after the Big Bang. Future observatories, both ground-based and in space, will push these boundaries even further, potentially observing the very first stars, the so-called population III stars, which were massive, short-lived, and composed solely of primordial hydrogen and helium. Gravitational wave observatories, like LIGO and LISA, are opening a new window into the universe, detecting ripples in spacetime caused by cataclysmic events like colliding black holes and neutron stars, offering insights invisible to light-based telescopes. These waves are providing direct observational evidence of black holes and neutron stars, helping us understand their dynamics and distribution, and even potentially testing the limits of Einstein's theory of general relativity. The universe is not static, nor is our understanding of it. We are in a constant state of discovery, continually revising our models and humbly accepting that the cosmos holds far more secrets than we have unraveled. The very beginning of our universe, the Big Bang, proposes a startling reality. All the matter and energy of our observable cosmos was once contained in a region smaller than an atom, incredibly hot and dense, from which spacetime began to expand. This primordial state, sometimes referred to as a singularity, is where our current laws of physics break down. It challenges our concept of before, because if spacetime itself began then, the idea of a before it loses meaning. The cosmic inflation theory addresses some of the Big Bang's puzzles, suggesting a brief period of exponential growth smoothing out the universe. But what powered inflation, and did it happen only once? Alternative models to the Big Bang exist, though not as widely supported. Cyclical or Big Bounce models suggest the universe undergoes endless cycles of expansion and contraction, with each bounce creating a new universe. Another idea is the ekpyrotic universe, where our cosmos arises from the collision of two branes, higher dimensional membranes, in a larger, hidden dimension. This scenario would also explain the initial conditions without relying on a singularity. The very first light detectable, the cosmic microwave background, is the oldest light we can see. It's a snapshot of the universe when it was only 380,000 years old, uniformly glowing throughout space, revealing its homogeneity and slight fluctuations. But this light offers more than just a uniform glow. The tiny temperature variations within the CMB are the seeds of all future structures, the slight density differences that gravity then magnified over billions of years into galaxies and clusters. The formation of the first stars, nearly pure hydrogen and helium, marks the cosmic dawn. These primordial stars reionize the universe, burning off the cosmic fog and paving the way for the complex structures we see today. Our understanding of the distant past also shapes our predictions for the universe's ultimate end. Will it be a cold, empty expanse where even black holes evaporate, or a violent rip that tears apart atoms? The Big Freeze, or heat death, scenario points to a cosmic future where entropy reigns supreme. All available energy is evenly distributed, leading to a state of maximum disorder where no work can be done and no life can exist. Another possibility is the vacuum decay hypothesis. If the universe's vacuum state is not its lowest possible energy state, a true vacuum bubble could spontaneously form anywhere and expand at light speed, fundamentally altering physical laws, destroying everything in its path. Such an event would be undetectable until it consumed us, providing no warning. It's a highly speculative but scientifically valid doomsday scenario, revealing the fragility of our perceived cosmic stability. Could the universe be a simulation? This philosophical argument rooted in computational advancement, suggests that advanced civilizations might run ancestor simulations, making it statistically probable that we are living in one of them. This idea challenges the very nature of reality, blurring the lines between what is real and what is simulated. It's a thought experiment that forces us to question our deepest assumptions about existence. The fine-tuning of the universe, again, plays a role here. If the universe's constants are so precise for life, it could be the set-up parameters of a simulation, carefully chosen to allow for the emergence of complexity. Or perhaps the universe is a giant, self-organizing fractal. Fractal cosmology suggests that patterns on smaller scales repeat on larger scales, eliminating the need for a definitive beginning or end and offering a self-similar structure at all levels. This would mean the cosmos is truly infinite in its detail and complexity. Every pattern we observe, from cloud formations to galaxy clusters, could be a manifestation of this underlying fractal nature, a universe within a universe, endlessly repeating. The universe is a cosmic engine generating complexity. From simple hydrogen and helium, it has forged stars, elements, planets, and ultimately, conscious beings capable of pondering its own existence. This generative power is miraculous. The anthropic principle also re-emerges here. We observe the universe the way it is because if it were any different, we wouldn't be here to observe it. It's a tautology, but it has profound implications for how we interpret cosmic fine-tuning. This leads to questions about consciousness. Is it a mere byproduct of complex neurological processes, or is it a fundamental aspect of the universe, emerging naturally from its intricate laws, perhaps even influencing reality? The universe is a tapestry woven from intricate particles and enigmatic forces. Higgs boson, the God particle, gives mass to other fundamental particles, filling the universe with a pervasive field that dictates how matter interacts with gravity. The existence of the Higgs field, confirmed by the Large Hadron Collider, underscores the Standard Model's elegance, yet it also opens new doors. What if there are other Higgs-like fields? Or particles of dark matter interacting via a dark Higgs? The mystery of gravity, its extreme weakness compared to other forces, also links back to extra dimensions. Perhaps gravity leaks into these higher dimensions, diluting its strength in our universe. The cosmic donut theory, also known as a toroidal universe, suggests a finite universe that curls back on itself, like a donut. If you traveled far enough in one direction, you might eventually return to your starting point, having traversed the entire cosmos. Such a universe might exhibit repeated patterns of cosmic microwave background or even ghost images of galaxies, light that has circled the cosmos multiple times. The search for these patterns is ongoing. The cosmos itself could be evolving, not just structures within it. Some theories suggest fundamental constants themselves might slowly change over cosmic time or even vary from one region of the multiverse to another. This varying constants hypothesis challenges a core tenet of physics and could dramatically alter our understanding of cosmic history and the conditions necessary for life in different epochs or universes. What is nothing? In cosmology, this isn't an empty void. Quantum vacuum is teeming with virtual particles, fluctuating in and out of existence, embodying a profound concept. Something can indeed come from nothing. This principle is foundational to models where the universe could have emerged from a quantum fluctuation in a pre-existing nothingness, essentially a universe spontaneously self-creating. The Pioneer anomaly was a baffling observation of spacecraft speeds subtly deviating from predictions as they exited the solar system, hinting at new physics. While largely resolved as thermal effects, it highlights the constant quest for unexplained cosmic behaviors. Unexplained fast radio bursts, FRBs, extremely powerful but very short bursts of radio waves from distant galaxies, are another ongoing mystery. Their origins are unknown. They could be exotic astrological phenomena or, provocatively, techno-signatures. The universe is a grand, evolving narrative, not a static picture. From its fiery birth to its accelerating expansion, every moment shapes its future, driven by forces both seen and unseen, understood and mysterious. This cosmic story is written in the stars, in the fabric of spacetime, and in the fundamental particles that compose everything. It's a story of creation, destruction, and continuous transformation on scales that dwarf our comprehension. Our existence, our very ability to contemplate these cosmic mysteries, makes us a unique part of this narrative. We are the universe's way of understanding itself, conscious observers within its grand design. From the bizarre quantum realm to the unfathomable depths of the multiverse, the universe continually defies our expectations, proving that reality is far stranger, more grand, and more wondrous than we ever dared to imagine. So what is the universe truly? It is not just what we see. It is a cosmic dance of dark matter and dark energy, a stretching fabric of spacetime, a field of quantum fluctuations, and perhaps one of countless other universes. It's a place where time bends, gravity warps, and the very concept of empty space is alive with energy. It challenges our intuition at every turn, forcing us to abandon our anthropocentric biases and embrace a truly cosmic perspective. This journey of discovery is far from over. Each new telescope, each new particle accelerator, each new theoretical breakthrough peels back another layer of cosmic mystery, revealing a universe ever more complex and captivating. The universe is not what you think, it is far more. It is a testament to the boundless creativity of nature, an ongoing symphony of physics and existence, continuously unfolding its endless wonders before our ever-curious eyes. Embrace the revelation. The universe you thought you knew is merely a shadow of its true, magnificent self, and the greatest wonders, the deepest truths, are still waiting to be discovered, patiently hidden in the depths of the cosmos. The true nature of reality might be fundamentally non-local, meaning things can be connected across vast distances without a tangible link. Quantum entanglement hints at this, but a cosmic-scale non-locality would be truly mind-bending. This could imply a deeper, underlying structure to the universe that transcends our familiar notions of space and time, offering a radical shift in how we perceive the universe's interconnectedness. Is the universe conscious? Panpsychism, an ancient philosophical concept now gaining renewed interest, suggests consciousness isn't unique to brains, but is a fundamental property of matter, present at some level throughout the cosmos. If consciousness is fundamental, the universe itself might be a vast, conscious entity, or at least its parts, possess an intrinsic, primitive form of awareness, leading to a startlingly alive cosmos. The cosmic loneliness argument posits that the conditions necessary for Earth-like intelligence might be so specific, and the timing so crucial, that we are indeed unique, at least within our observable cosmic horizon. This singularity places an immense responsibility on humanity to safeguard and propagate life, as we might be the torchbearers for conscious existence in this corner of the vast, potentially empty, cosmic ocean. The sheer scale of cosmic time also defies intuition. Billions of years have passed since the Big Bang, and billions more stretch into the future. Our human existence is a mere blink against this backdrop of cosmic epochs. The journey of a photon, carrying information from distant galaxies, can take billions of years to reach our telescopes. This light is a fossil, showing us not the present, but the universe as it was in a bygone era. The search for technosignatures extends to looking for signs of stellar lifting or Dyson spheres, megastructures built by advanced civilizations to harness immense stellar energy, visible as unusual infrared signatures. The universe is a cosmic playground for extreme physics. Merging neutron stars create gold, and other heavy elements through rapid neutron capture, enriching the cosmos and providing the building blocks for jewelry and electronics on Earth. Even the expansion of the universe allows us to see this progression. Distant galaxies are highly redshifted, their light stretched by cosmic expansion, revealing their extreme age and the early universe's more chaotic state. The universe is a dynamic puzzle, constantly evolving, revealing new layers of complexity and wonder. Its very fabric, its subtle biases, and its grand structures all hold clues to its ultimate nature and origin. From the cosmic beginning to its possible ends, from the smallest quantum fluctuation to the largest cosmic web, the universe is a symphony of forces, particles, and phenomena that defies simple explanation. It challenges our every assumption, expands our every horizon, and humbles us with its boundless immensity and intricate beauty. This revelation is not an end, but an invitation to endless wonder. The universe is not what you think. It is far, far more. And as long as humanity continues to question, to explore, and to dream, we will continue to unravel its magnificent, mind-blowing cosmic revelations.